Okay, great. So yeah, I decided to, based off the timing, I decided to focus in on one specific part of the work that I've been doing that's more relevant to the computational models. So in this talk, I'll talk about generating synthetic labeled data from existing anatomical models, specifically with reference to echocardiography segmentation. And this is an example of looking at the synergies in between some of the mechanistic models that, for example, Maciej talked about earlier with deep learning and statistical modeling. So this project was to generate realistic looking ultrasound images with a known ground truth to facilitate training of deep learning algorithms. So that's kind of the basis that we're starting with. And for those of you not familiar with ultrasound, ultrasound is a widely used imaging modality for diagnosing cardiovascular disease, and it's used because it's real time and has a high temporal resolution with no ionizing radiation. And this is an example of one echocardiography image. And what we've seen in the past few years is that deep learning has increasingly being used and integrated into ultrasound workflows for automating all sorts of measurements and pieces of the diagnostic pipeline. So that might be segmentation, denoising, view classification, measurements, and even diagnosis. In this talk specifically, I'm going to use segmentation as an example application. So an example is shown on this slide where you have an input image and you're trying to segment important features or regions of the heart. So in this case, we have the left ventricle and the myocardium and the left atrium. But what we see in general is that deep learning algorithms are only as good as the data that they are trained from. So in ultrasound, that's particularly hard because generating high quality annotations of ultrasound is difficult and time consuming. So you might have some images that are fairly good image quality, such as this one, you can see the structure boundaries relatively well. And then you often have other images where there's some sort of dropout due to shadowing caused by the ribs, caused by other things, difficulty in acquiring a proper image, and then it becomes difficult to actually acquire those annotations. And that's a problem because the deep learning algorithms are only going to be as good as the data that they're trained from. So we really need high quality annotations for training deep learning algorithms that will work in practice. With that said, most efforts to build an echocardiography dataset have relied on annotators label images. So the pros of this approach is that it matches the clinical implementation. So you'll have, this is the way that things are actually done clinically, so it makes sense to do it that way. The cons are that it's expensive and time consuming. It takes a clinical expert, a long time to go through each of these images and perform the annotations. And so it's labels because a quite large set in order to train the deep learning algorithms. The other con is that there's usually high inter and intra-observer error because of differences in standards, differences in protocols at different institutions, and because of the lower image quality that you see. And if you would need to adjust it to meet new guidelines, it's quite difficult to do if you have manual annotations because those you have to basically go through and relabel all of the images that you have again. So instead, we want to build images from high quality ground truth labels. So we want to start from labels and then build the images from that. And the pros of this approach is that it's easy to scale and the labels can be adjusted later. And as long as we know that we're starting from high quality labels, we know that we have those already, so we don't have to worry about that. And then the cons, of course, is the big question here is how will that perform? How will a network trained on these images perform? But yeah, so the question then is how are we going to get these high quality ground truth labels? Where are we going to start from? And for this, we looked at some of the work that's been done by my colleagues in London. So computational models have previously been developed for research in a variety of areas. So you saw an example already from Maciej of shape analysis. I'm sure there's going to be talks later on electromechanical simulations and fluid dynamics as well. So we have these computational anatomical models that have already been developed for a wide range of applications. And the goal here is the idea is that we can use these models as sources of annotations. So that's what we're going to start from these models that have already been developed and use those. And so this is generally the pipeline that we've developed, which is to move from meshes derived from CT images to a database of artificial ultrasound images with paired labels. So again, that's the overall goal here, but I'll go through this in each of these steps in a little bit more detail. So starting from the original models that we wanted to use, so I showed that we're going to use some anatomical models to start with, and we got these from 20 models which were developed from CT scans of asymptomatic adult hearts. So these were derived segmented semi-automatically by, again, our colleagues at KCL. And the reason that we have confidence in these is that CT images provide a much better spatial resolution, allowing for high quality annotations. So you have a much better idea of where the boundaries of different features are from CT images than you do from ultrasound. Okay. So the next step in this was to extend the original model set with new shapes. So as I mentioned, you typically need a large variety of images to train a deep learning algorithm. And the original model set was only 20 models. So we wanted to extend this to a larger set to include additional variability in the data set that we are generating. And so Maciej already gave a brief overview of this, but this was using principal component analysis to generate new models from our existing set of models. So the way that works is each model is meshed, and we use principal component analysis to find the primary modes of variation. So what I mean by that is that we have 9 modes which show different variations of how the shape is changing. And we can do that. So, and those each encompass like a different axis of shape change. And then what we can do is we can randomly sample from each of those modes, each of those axes of shape variation, and that will give us a new model, which is, again, is taken from the set of realistic possibilities, but is a new anatomically realistic shape that adds additional variability to the data set. So we can continue to do this until we generate enough models that we have sufficient anatomical variability. So we continue to just randomly sample from these modes of shape variation. Okay, and then the next step is that we're going to use this for an analysis of 2D image segmentation. And so we have to extract a set of what I call pseudo images and model labels that match the segmentation task that we want to perform. So that first starts with extracting a set of 2D slices that are the same view. In this case, it's an apical view. And then it's extracting a set of pseudo images and labels corresponding to that, to those slices. So again, the example application is segmentation in apical and 4 and 2 chamber images. So that's an example shown here, both from the model. On the top, you see a apical 2 chamber image, and this is an apical 4 chamber image, and then here in real ultrasound images. So this first one is a apical 2 chamber image, and then these next 2 are 4 chamber images. The way we do this is we slice the models by finding relevant landmarks within the models that correspond to things that should be found in the real images. So in this case, specifically for an apical 4 chamber image, you should have the mitral valve, the tricuspid valve, and the apex. So we find those landmarks in the model, and we use that to pull out a slice. Then we orient the slice and position it within the real ultrasound cone in the same way that would be in a real image. And then we just perform a number of appearance transforms to kind of add some noise and reduce the hard edges in the image. So that's how we generate this final pseudo image. And of course, at the same time, from this slice, we have the ground truth label as well that we can generate. And you have to include modes of variation that correspond to the modes that you see in real images. So there's a number of those, but I'll just go over one or two briefly here. So one example would be in real images, you're usually either focused in on the left ventricle or you're focused on the entire heart. So in the images highlighted in blue, you see this one's more focused just on the left ventricle. And then we had to generate some pseudo images that matched that. So we're more focused on the left ventricle. Alternatively, you can have images that are focused on the entire heart, showing all of the chambers. And we also generated pseudo images that mimicked that distribution. And another axis of variability is how the slice is extracted. So in most cases, you're not going to have somebody extract a perfect 4-chamber slice because there might be slightly foreshortened, which means they didn't get the apex exactly, or it might be slightly rotated or something. So we also simulated this in how we extracted the slices. We didn't extract perfect 4-chamber slices every time. And again, that added additional variability to the data set that we are creating. So in total, in this step, we built a data set of pseudo images and labels from these original and anatomical models. And one thing that's important to notice here is that we started from a small set of just 20 segmented models, and in each step, we're adding additional variability and increasing the data set size. So with the new shape models using the principal component analysis, we increased to 100 synthetic models. And then with those steps that I showed earlier in generating the pseudo image, in how, which chamber we focus on, how we extract the rotation, how the slice is positioned, we add additional variability. And we end up with a data set that's, in this case, 900 images. It could be arbitrarily big. But of course, you start to then probably have some replication in the variability that you're creating. But we've created quite a lot of variability here with these steps, and we end up with a much larger data set. Okay, so the next step is to use the pseudo images, and we're going to transform them to be more realistic compared to how real ultrasound images look. And this was done using a cyclogan. So for those of you that aren't familiar, generated adversarial networks are used to generate realistic looking images. And typically the standard model is that you just input a noise vector, a generator network takes that noise vector and generates an image. And at the same time, you have another network called a discriminator network that is looking at the difference between the generated images and a set of real images. So in this case, cat images. And these networks are kind of competing. So this one's competing to create as real images as possible, and this one's competing to try to say which one's real, which one's fake, and they learn at the same time. And this is, in general, been proven to have very good results in terms of creating realistic looking images. Now, conditional GANs can take an image as well as that noise vector. So you can have the network basically conditioned on an image. You want to, instead of just taking the noise vector, you want to generate something that has something from the distribution of this input image. So in this case, you might be generating, a map, like a Google Maps style image from aerial photograph. And cyclogans combine two conditional GANs for unpaired translation between two different domains. So the authors who originally proposed this showed it for horses versus zebras. So they showed that, using these two conditional GANs, they could translate an image of a horse to an image of a zebra, and vice versa, an image from a zebra back to an image of a horse. And what we're going to do is instead we have one domain that's the pseudo image domain, and one domain that's the domain of real images. And we use the cyclogan to translate back and forth in between those domains. And the way that the training works is you have a real pseudo image. It goes through one of the networks to a generated ultrasound image, and then back through the other network to a reconstructed pseudo image. And the first loss in your training is a cycloconsistency loss. So you should have the reconstructed pseudo image should look identical to the one that was originally input into the network, and then the network will receive some feedback if it's not identical. The second loss is that adversarial loss component that I discussed earlier. So if you have a real ultrasound image and a generated ultrasound image, you have some sort of, you have a discriminator which is trying to tell, the difference in between those. And then hopefully this generator is learning to generate as realistic looking images as possible. And you do the same thing, going through the cycle the other way. So starting from real ultrasound images to a reconstructed ultrasound image and going through a pseudo image in the middle. Okay, so in terms of network architectures, it's pretty standard architectures that we used here. So the generator is just a UNet and the discriminator is a simple convolutional network called a patchcan. So nothing fancy there. And I'll give you guys a little bit of an overview of some of the important things that we noticed when we were training. So it was important to replicate strong image features in both domains. So this in real ultrasound, you have a strong image feature here, which is called the pericardium. This is for a different ultrasound view, but just to demonstrate the point. And originally in some of the pseudo images, we did not include this pericardium, which meant that the lateral wall here was interpreted as a pericardium because it was the strongest image feature that was present. So we had to end up actually including the pericardium within the model to kind of mimic the strong image features in both domains to get the accurate translation in between those domains. The second thing that we noticed during training is that we had some mode collapse, especially with the valve. So this is an example image taken early in training from every 5 epochs. And you see that there's this consistent feature that's always present across all of the images, no matter what the other anatomical features are doing. So this valve is present no matter in the same location, no matter where no matter where the actual ventricle is. And that's because in the models, the CT images don't have enough resolution to actually include, to find the valves, to see the valves. So the valves are just modeled as these flat slabs, which is of course not comparable to how it is in real echocardiography images. So what we did here was we kind of just removed the valves in some of the pseudo images to allow the model to generate realistic looking valves itself. And that we saw that helped a little bit. And then the final thing here is that image quality fluctuates between epochs, so you have to do a qualitative evaluation of which epoch you actually want to use through the course of training to find where the best one is, because sometimes you do have that mode collapse, and so you have to kind of look through manually here. This is the one manual step in terms of finding which cyclogan epoch to use. So in implementation, we used 5 different data sets to test this out. There's numerous examples of deep learning methods failing when they trained on one data set and tested on another data set. So we tried to do this with 5 different data sets to prove that it would be applicable across different data set domains. And you can see that there's quite a bit of difference in between the appearance of some of these data sets, particularly in between this CAMUS data set and the EchoNet data set. So these first three were used for training, and these 2 training and testing, and these last 2 were left exclusively as test sets. These are some of the results of the synthetic data generation. So these are 6 images. I'll let you guys take a look and see if you can figure out which ones are real and which ones are fake, depending on, yeah, I guess if you're familiar with echocardiography images, you can probably tell. If not, you might not be able to. So okay, I will give you answers now. So this first 2 are real images, then this one's a fake image. This one is a fake image as well, real and fake. And you can probably tell in real ultrasound images, there's some variation in the noise patterns throughout the image, which has to do with the way that the ultrasound images are formed. And that's not the case in the synthetic images. So that's one thing to improve. Okay, looking at some results. So this just shows that although we did not specifically enforce that the structures had to match the original label, that was not enforced in the training process. We see that when we overlay the labels on top of the synthetic images that were generated, we still get a very close match in between the structures that were generated and the label. And we proved that later as well, but this is just showing that qualitatively. So that was a good thing. We showed that we didn't have to actually enforce that in the training process. Okay, final step here. Can we use the synthetic images to train a segmentation network? So we want to actually train a network with the synthetic images. And so we just use, again, a standard segmentation architecture. This was a UNet, so nothing fancy here. And the comparison here is we have one network that we're going to train with synthetic ultrasound images and the labels, and we have another network that we're going to train with real ultrasound and labels because we had data sets of real ultrasound and labels here. And then we're going to test both of them with real ultrasound, and we're going to look at with the same data set of real ultrasound images, and we're going to compare the performance here. So that's kind of the comparison that's being made. So showing some results of that. First, just looking at an inter-observer comparison. So we see that if we check how observer does versus the real data, it's about 88% dice score. Dice score is just a measure of the overlap in between the two different segmentation areas, in between the one that's predicted by the network and the one that was originally labeled. So we've got about an 88% dice score for an inter-observer number versus 91% for the observers looking at the synthetic images. So that again shows that the synthetic images matched what observers were looking for in terms of the structures that were generated. Now this shows each row here is a different network. So this was a network, the first row is a network that's trained on real EchoNet data and then tested on real EchoNet data, and then trained on real CAMUS data and tested on real CAMUS data. And what we see here is that, of course, the one that's trained on real EchoNet data and tested on real EchoNet data is the one that does the best. So it has about a 94% dice score. But for the other ones, the one that's trained on synthetic data has a comparable performance to those trained on an alternative data set of real images. So for EchoNet, it's comparable to the networks that were trained on Site A or CAMUS. For CAMUS, there's slightly lower scores. Don't really have time to get into that, but there's some reasons for that. And then for Site B, the synthetically trained network actually did the best here. So it had the highest dice scores, and for the pathological data set, it was somewhere in the middle in terms of it. But in general, the general trend that we see is that a network trained on synthetic data is about as good as a network trained on real images from another data set. So that's an encouraging result. Okay, this just shows qualitatively some of the results. So the red here is the label, the green is the network trained on real data, and the blue here is a network trained on synthetic data. So you see that in some of the worst cases, the network fails. In this case, you have a poor quality image, and it's probably fooled by the valve, what looks like a valve here. And in this case, you have maybe a feature that was bulging septum. So it's not really, that's maybe a pathological feature that was not included in the real data sets. And here you have severe left atrial dilation. So the network was fooled there, but in this case, the real network also had the same results. So, but in general, the network did quite well. The median images were quite good, and this shows kind of distribution over each quantile of dice score for all of the networks, and you can see that there were some failures on the low end, but in general the results were quite good in terms of how the network was able to find the relevant features, even though it was trained on synthetic data. Okay, so in this we proposed a method to generate realistic ultrasound images with a known ground truth to facilitate training of deep learning algorithms. And we demonstrated performance that was at the same level of inter-observer error and inter-dataset error. So that was kind of the overall message from this. Future work will be extending this to 3D data, applying it to new views and applications, and adding a temporal dimension to the generated data, because of course that's one of the strengths of the ultrasound is that it has that high temporal resolution. So we would like to include that in the generated data. So with that, thank you very much. Thank you in particular to my colleagues at KCL, Cristobal and Maciej and Pablo, for their help with this project. And any questions?
Okay, thanks a lot, Andy, for the presentation. Is there any question for Andy? Yes, Cameron, please.
Hi, Andy. Yeah, great presentation. I'm just wondering, in the training sets for generating the synthetic images, were the images all acquired on the same ultrasound system, or do you know from different sites, were they using different machines?
Yeah, so I'm not sure. I mean, that's why we use different data sets in general, was to try to get variability both in whether the ultrasound system that was used and the practices that were being used. I'm not sure off the top of my head which systems were used for which data set, but I can say that it seems, I'm pretty sure for the EchoNet it was a Philips system. Of course, for some of the internal data sets we used, it was a GE system, and I'm not sure for CAMUS. And we did, so I think there's sufficient variability in the systems that were used, and we also saw a high variability in the appearance of the images.
Okay, cool. That's great.
Is there any other question for Andy? Jorge, yes, please.
Hey, Andy, thank you for the presentation. So when comparing this synthetic image versus the manual segmentation, in the training, do you use the same number of images synthetic versus the other one?
Yeah, good question. Let's see. So it depends on the data set. So we had about 900 images in the synthetic data set. The EchoNet data set was a data set of 10,000 images, and that was divided 80%, 10%, 10%, training validation test. So that was 8,000 images. Whereas the Site A data set was just 400 images. And the Camus data set was about 1,000 images, if I remember, maybe 1,200 images, if I remember correctly. So we did have a pretty good big distribution in terms of the real data sets, in terms of the number of images in each one as well.
Because on the one hand, for fairness comparison, you could use the same number of images, and since generating synthetic images for free, you could do so. But on the other hand, you can also claim that synthetic images are unlimited, and you could claim that the advantage is precisely that, the fact that you can use infinite number of images in the training, so the models convert to potentially a more efficient solution. Or
yeah, definitely. Although I think you get like diminishing returns eventually from including more and more synthetic images, because you're not getting that much variability since it's coming from the same baseline models. So it might just end up making your training take longer. We did a few studies with the data set size, and it did seem that it was converging. The results were converging based off. We weren't going to get much more performance improvements from using additional synthetic data.
And the other question that I have is regarding the training of the cycle gun. So I'm assuming that you go for several epochs, right?
Yeah.
And my question is, why then constraining to 900 images? Why not using more and each of the epochs feeding with different new images?
Constraining to.
So let's say that you in the cycle gun you fed the 900 image for one epoch, then you fed them again for another epoch, and so on and so forth, right? My question is, why not each of the epochs use a different set of synthetic images?
Yeah, you could do that for sure. Yeah, and that might actually help. It was just then you would have to kind of implement a pipeline where you were extracting the images real time while you were doing the training, I guess. Or otherwise you ended up just extracting, it's 200 epochs, so you end up extracting 200 times 900 different image sets for each epoch. So it was a little bit of just data management there, but you could implement it so that you were real time extracting the images, the synthetic images you needed from the models while training the cycle again.
It depends on your generation speed, but in any case, you could also generate them offline and then upload them to the training each time that you go to another.
But that's what I was saying. It's a little bit of a function of data set size, because if you have 1,000 synthetic images and you're training for 200 epochs, you could do it.
So in my case, it's a different project, but it's for these deformations models that I do for augmentation, and this is precisely what I'm doing. Each epoch is fed with totally new images, and in our case, it converts to a better solutions that just reusing the same epochs. Okay. Because even though you are constrained to a certain variability that you are generating with the statistical models, and also with these variations, mimic appearance, and this stuff that you have included, in the end, if you use different images, you may help to pick up those variations even more.
Yeah, no, that's a good point. It's definitely something we could try.
Cool. That was all my comments. Thank you, Andy.
Okay, thank you.